Okay, I'm a professor of computer science, which is always kind of funny because none of my degrees are in computer science at all. And ultimately, I do I've done classes on machine learning and computer architecture. That mix seems to fit me nicely. And yeah, I've been there since 2000, so I guess I must like it. With great difficulty. You know, it's how long is this piece of string? Obviously there's a lot of things associated with knowledge-driven approaches. And personally, I don't get involved in that, but there's a lot of great things happening there, particularly with ontologies. And on the flip side, obviously, I'm more interested in things that are adaptive. And that's ultimately where I sort of came to land. But actually my PhD's in neural networks. So you know, I sampled neural networks, fuzzy logic, and then finally landed in evolutionary computation. You've got to try things out to really find what fits. And what is AI? It's a bit like it's being able to map from state, whether state is external on its own or external and internal, which is interesting. So mapping from state to decision without consciousness. There you are. My work being guided by evolutionary algorithms. Maybe I can rephrase it from the point of view of what I like with evolutionary algorithms is it's a very open framework, and it gives me the unexpected, and the unexpected is interesting. So I don't have a problem with gradient methods. I was, let's say, brought up on gradient methods. I just find them a little, they give brilliant results, but philosophically I find them, let's say, constraining. In that respect, you see, this is where you get different things happening. Deep learning results are really interesting. They've really pioneered what is possible. And let's face it, before 2015, it wasn't considered that you could actually build agents directly from frame buffers. Whereas now it's taken for granted that, sure, you can build agents straight off the frame buffer. At least for some applications. It's just a matter of time before we get to do it for any application. I think where potentially deep learning struggles is getting simple solutions. I hesitate to use the word elegant, but to blow my own trumpet, yeah, elegant. So where the evolutionary methods, I think, have came out with a significantly, again, is it better? Because from the point of view of the quality of the policies, I think it's a wash. But in terms of simplicity of the solution, I think evolutionary methods have really something to demonstrate. To the point where you can execute these solutions on very small footprint devices. Okay, so from that point of view, I mean, there are lots of them. There was one poor undergraduate I had that was trying to define a spaceship, so a policy for controlling a spaceship in a physics world, and he was being chased by opponent spaceships that observed a flocking algorithm. And we had this running for a week, and the flocking, pursuing spaceships had not found our single spaceship, so we thought we were onto something. And it turned out all we'd done is discovered a physics error in the world. So our spaceship had disappeared down a black hole synonymous with a rounding error someplace, and none of the pursuing spaceships had managed to find this. Needless to say, that wasn't the answer we were looking for. Another case of that was, I think we were looking at one of these classic kind of robot control tasks for a two-link robot arm. It's actually called the Acrobot. Now the Acrobot had a result where the best case was actually a very specific sequence of actions that were found by deploying A star. Now A star is optimal. So fine, we thought, well, okay, this is the best possible solution. Can we evolve a policy that finds it rather than just being a brute force search process? And you know what? We actually managed to get a couple of steps faster than A star, which didn't make any sense, shouldn't be possible. But it turned out that actually A star's quality is all driven by the quality of the distance metric assumed, and there was a small error in the distance metric that no one had noticed before. And this result had stood for about 13 years before we'd managed to figure there was a hole in it. So unexpected is good. Okay, so in that respect, kudos actually to my wife, Nursinja Heywood, who's also a professor in computer science. Her specialisation is actually in security, so occasionally she gets me to sort of, let's say, we co-evolve some approaches. And in some of our early work there, I suppose the earliest one was evolving buffer overflow attacks. So this is probably about 2005-ish, with a student, Ganesh Kaijuk. He's now, where's he now? He's out in California, Silicon Valley, doing more of this. And ultimately, it meant that we were able to first identify the instructions that a typical application would use, just by looking at what instructions it sends to the operating system. And then we could say, well, this is the subset of instructions that a regular application uses. So can we go away and define an exploit using that regular set of instructions? And to make life interesting, actually what we could do is we could let the evolutionary process evolve the candidate exploit and then feed it back into the detector, look at the alarm rate, feed the alarm rate in as our fitness or performance function, where the goal is to minimize the alarm rate while still designing a valid exploit. And lo and behold, you could actually do this. So that was sort of an interesting case of what's called vulnerability testing. And that then sort of promoted better design of detectors, which now arguably you can't use that approach at all. Care of far better buffer overflow checks inserted into compilers. So that's all good as far as I can see. Well, dare I say, follow the money. Now, does that mean take your pick? So autonomous cars. If evolutionary computation could be at the center of solving things like algorithms for driving cars around people, that seems to be a big ticket item. Driving cars under crazy weather conditions. There's all manner of aspects. It's an open-ended domain, and to my mind, the more open-ended the domain, the more interesting it gets. So I think that would be a real wow factor. Oh, specific problems. Where does curiosity come from? Okay. So things like curiosity are actually very important. I'm not trying to build a better human. I mean, that's just plain ugly. What I'm interested in is can an algorithm sort of identify goal-driven behavior? Where does goal-driven behavior come from? At what point do you be less goal-specific and more exploratory, quote unquote? So there's I think lots and lots of very open-ended things to be done there. Where does it go next? Hopefully there's no end to that. All you do is, I mean, the most interesting things are the things you stumble into. You know, it's all well and good to, I don't know, produce a better widget. I mean, there are so many open-ended things, even looking at computer hardware. I mean, increasingly people are using evolutionary methods to design code. Now, why is that related to hardware? Well, hardware's got so fiendishly complicated that we as humans can't necessarily design the code that utilizes all of the capabilities of the hardware. So there's so many things that are just waiting to happen, I think. And I think we're just going to see an acceleration of more interesting things happening. And I see no reason why evolutionary computation can't be the center of it.